Welcome to this lecture number 5 of this series of lectures on electric machine design. In today's lecture, we will talk about core design. We will talk about how laminations are stacked in a transformer, and we will also talk about how the yoke is constructed. So, as you all are aware, that core is the basic block over which the windings are wound, right? And it is made of steels. So these steels are laminated sheets, and these sheets are put together and arranged to form what is known as the core. So if you have a transformer like this, if this is a typical transformer core, and the laminations, this core is made up of laminations of these steels, and if this is the window, the windings are wound on this around this core, and this basically holds the whole structure of the transformer together. Now, these these laminates, these laminations or laminates, these laminations are about 0.33 to 0.5 mm thick, and they are made of transformer grade steel. And this is either hot rolled or cold rolled. We have studied these two types in the previous lectures. The hot rolled steel permits a flux density of around 1.45 Weber per meter square, whereas the cold rolled steels permit a flux density of around 1.8 Weber per meter square. This is a bit costlier. Making this cold rolled steel is a bit costlier than hot rolled steel, but the advantage is that it permits a higher flux density. Then on the top of on these laminations there is a coating of materials known as kaolin, varnish, or phosphate base coating. Okay, and these are these coatings are applied on each laminate, and then another layer is put on top. Now we talk about the cross section. The core cross section. And for small transformers, small core transformers, small transformers, they have a rectangular section, right? By rectangular section I mean that if you take a look at a small transformer from the front, it will look something like this. The front view of the core is going to look something like this, like a rectangle. However, for large transformers, it is ideal and it is desired that the core cross section be a circle. And why is that? This is because the circle has minimum periphery for a given area. What does this mean? That the circle, if you have a circular cross section, if you have to lay a wire around this cross section, this would result in minimum length of the conductor. This is denoted by this length LMT, which is the length per mean turn, length of mean turn. All right. So this results in a circular cross section. Circular cross section results in a reduced amount of conductor material. This so if you have copper as the conductor, so a reduced amount of copper will naturally bring down the capital cost of the transformer, right? Another advantage of using a circular core is that in case of short circuit conditions, like I mentioned in the previous lecture, there are forces, radial forces act on the windings when they are subjected to short circuit conditions. So in this case, what happens? There is no tendency of deformation. The tendency to deform is very less. To deform is very less in circular cores, but in rectangular cores this same is not true. So rectangular cores are subjected to these deformations, so that's why it's recommended to have a circular core cross section. When I say recommended, I mean it is ideal that you have a circular cross section, but this comes with a drawback that having a completely circular core results in increase of the lamination cost. Okay, so if you have the circular core has the advantage that it gives you lesser conductor cost, and it also prevents this deformation forces, but the drawback is that it leads to an increased lamination cost. So what is done? A compromise is a compromise. What is this compromise? We use a stepped core. Right? So what happens with a stepped core? We use two lengths, two sizes rather. what is done in this case? We have the core is made in the form of a step. I'll show you this graphically in a bit. And this core, the corners of this stepped core, corners of the stepped core, they lie on what is known as the circumscribing circle. Circumscribing circle. And this core, this stepped core, is known as the cruciform core. Cruciform core. Okay. So now I'm going to show you graphically what I actually mean by this stepped core and rectangular core. In the first case, the core is if this is the core, and you have the and if this is the LV winding, if let me draw this here, if this is the core and if this is the LV winding, you have a duct on the outside, I'll show this duct as a two-layered duct. Let's call it the duct. And then you have the HV winding on the outside. This is a sort of a top view of the winding of what? Of the rectangular core. In contrast, what do you have in the cruciform case? You have something like this. You have just a second. You have the core is something like this. So you see that and this boundary this is known as the circumscribing circle, this circle on the outside, circumscribing circle, right? And you have the LV winding encircling it. All right, this is the LV winding on the outside. This is followed by the duct. This is the duct. This dashed blue is the LV winding. And on the outside you have the HV winding. So this is the diagram of a two-stepped cruciform core. Okay, so this is the difference between the two cores. This, I said earlier that this is used for smaller transformers, and this is used for larger transformers, larger power transformers. Okay. Next, we move to construction of the core and how this core is constructed actually. Core construction. So for smaller transformers, the complete magnetic circuit can be punched as a hole, but this process would lead to wastage of steel. Also, winding on this transformer, if it's made as a whole, would be difficult. So what happens in larger transformers, what we do is the coil is made separately, and then it is placed on the assembled core. Okay, so what do I mean by this? Let me show you graphically. What we have is are different types of laminations. We have I-type laminations, and we have E-type laminations, and they look something like this. You have laminations like this, okay? So this is known as I. Why is it known as an I? Because you see, if you see from this part to this part, it's like this bar. Then if you see from this part to this part, it's like another I, right? So these are all I-type laminations. Okay, so what you do is you have the first phase is like this. You have one eye here, another here, another here, and another here, and in the next layer on top of this you will have this like this. So it will be like the next winding will be in the next section will be on top of this, right? So it will be from here to here. You will have another section, this will be another section, and this will be another section, and this will be another section. So that what happens, this is wound in layer after layer. Okay, the next type of lamination is the E-type lamination, which is like this. Okay, it looks like the letter E. This lamination looks like the letter E. Okay, we call it the E type, call it I type. Okay, then we have the L type. So it's like this. You can see this is the letter L, this is another letter L, inverted L, right? And this is the L type core. And the next type is the shell type core, the core of the shell type transformer. It is like this. So it is like this. You have this break here, this is like this. So you see that there are different sections. This is one section, this is another section, this is another section, and this is another section. So this is the shell type, the core of the shell type transformer. Okay, fine. So what you do in this core construction, you have, let's say, an I section. You have this I, okay, then you get another I like this, okay, then you put another I over here, and you put another I like this. So this is hidden, this inner eye is not visible. I mean, you cannot see this, so it's something like this. So if you see from the top, you will you see that it's something like this. Okay, so do you understand? So this is the one layer, layer 1. What is the second layer? The second layer will be like this. It will be, since the underlying joint was exposed, next layer will be like this, on top of this, right? It will be, let me show you it with two different pictures, so you will better appreciate this. If you have the first position is like this, the first layer. It's the first position, or it's also called as the odd position. what is the next position going to be? It will be different than this one. How is it going to be different? I'll show you. Like this. So do you see the difference? If you see this point and this point, this lamination was like this, the blue lamination was like this, and in the next layer it will have a green lamination on top like this here. So this is the second position, or the even position. Okay, so this is how these laminations are laid out. Okay, there is this concept which is known as interleaving. Interleaving, this is the process of interleaving, where you have one lamination arranged one way and the other lamination arranged in the opposite way, right? This is this process. So what happens, this is basically you have to joints between the limbs and the yoke. Since I have told you last time, this is the limb of the transformer and this is the yoke of the transformer. So you have laminations one on top of the other like this. Then you have the other one over this, right? Then you have the next one over this. So this is known as interleaving. Why is this interleaving done? This interleaving is done to reduce air gap. By this process of interleaving, you basically give a smaller effective air gap for the flux to jump. What happens because of this? Let me just erase this first. In small transformers, the path of the flux is small, right? So if there is air gap between the joints, it is relatively much more important than large transformers. So for these small transformers, the air gap is of, since the total length of the flux is, the length of the path of the flux is very small, air gap is also very important. So you have to take care of this air gap and you have to reduce the air gap. So how do you reduce the air gap? You do that by interleaving. Okay, so at best it is done one step at a time. Right, you have one section, then you place another section on top of it, right? Then you place the second section on top of this. Then you do the second section like this, right? This process is repeated until you get the desired width of the core. Okay, so this is done one at a time, and this is usually done in smaller transformers, this one step at a time. But if you have a large transformer, going this one by one is going to be a time consuming process. So what you do, you have some numbers of, let's say, up to 20 laminations. You get them together, you lay them out like this, one up to 20, and then you get another 20, you stack them on this, and then you put the other 20, right? So this is how this what does this process do? This reduces the assembly time, and this minimizes risk of imperfect interleaving. Okay, so since these interleaving laminations, they will also have some air gap. Any gaps in the interleaving will lead to an increased magnetizing current IM, and this increased IM is going to be responsible for increased iron loss. So this gap in this interleaving should be around 1 to 2 mm only. Okay, next we move to yoke construction. And if you remember correctly, yoke when we talk about cores, this is the limb, the left hand side, left hand right hand side are the limbs, the top and bottom parts are the yokes, right? So this yoke, it has a cross section of around 1.15 times the limb. Okay, the cross section area of the yoke is around 1.15 times the limb cross section, and this is done because this reduces the flux density, which reduces magnetizing current, which reduces the iron losses. Okay, so here you can have a higher and increased cross-sectional area, since you know that there are no windings on the yoke. Since there are no windings on this part and this part, you can increase the cross-sectional area without affecting this LMT, which we talked about in the last class. I mean in the earlier segment, this mean length of the conductor. So you can increase this area, the area of the cross section of the yoke, so you can increase that safely. But what happens because of this But what happens because of this difference in the cross-sectional area? There is this phenomenon which is known as cross-fluxing. What happens? You have flux which goes in one direction, and because of difference in area, it sort of splits. So you can think of this like you have a conduit. You have a conduit, and there is constant flow of water in it, right? So you have, let me just draw it in a better way for you. If this is a conduit, and if there are, if this is the incoming channel, and you have the outgoing channel like this, so area of this incoming channel, if the area of the incoming channel is the same as the outgoing channel, the flow is going to be normal. And this is the common area. This area is the common area. And if opposed to this, if you have a situation where you have the incoming path of a particular area, and you have only two outgoing channels, so what is going to happen inside this common area? You will see that there's going to be, if this is like this, normal flow of water is going to be seen. But here you will see that at some points you will see that there's going to be turbulence, right? So this is turbulence. So this happens because of what? Because of difference in area. So why do we have two different areas? We have two different areas because we want to reduce the iron losses. But on the other hand, this is counterproductive because cross-fluxing leads to additional iron losses, right? And this cross-fluxing leads to iron losses. This leads to local overheating of the core. So how is this problem being taken care of? We go for a technique which is known as yoke stepping. Yoke stepping. So because of this yoke stepping, what we do, we mitigate this problem of cross-fluxing, right? We obtain the objective of having reduced iron losses, and we sort of equalize the flux distribution. We call this term as yoke stepping. So it equalizes flux distribution in the core pockets, and reduces additional iron losses. Okay, so how do you do this yoke stepping? Let's see. You have a This is the rectangular section. You have the this is the cruciform section. The next type is you have with a step upwards, and the third type of construction is with a step downwards. Okay, so this is how you try to mitigate the problems associated with having an increased area of the yoke. Okay, so once you are done with stacking these laminations together, you have to go for clamping the core. Clamping the core. What does this mean? You have iron frames between which the core is, the laminations are sandwiched, are placed in between. Okay, what you do, you punch holes in the laminations and you have bolts. You have bolts, right? So I'll show you this graphically. So we'll have bolts which go into the laminations, and of course these bolts have to be insulated from the side plates and the laminations. Side plates and laminations. Which otherwise may lead to short circuit of the core. So you use insulated bolts. You have to insulate the bolts from the core. So how is this clamping done? I'll show you. So if this is your core, right, you have an iron bar going like this, right, and then this bar extends from the other side as well. So in between these two bars you have this, and you have bolts here, and you have a similar construction on the bottom as well. Okay, and then you may have some additional reinforcements in the form of brackets here and here and here. So this is how you clamp the core. Okay, so with this we come to the end of this lecture on core construction. In the next lecture we will talk about how windings are designed. I hope you have understood whatever has been discussed in the lecture. If you have any queries or questions, you're free to ask me. You can ask me via mail or in the comments of the Google Classroom. I hope you are reading and following up with the lectures by reading from the book as well. And we'll see you in the next class. Thank you.